Third project, and now the stakes are as high as they get, a medical diagnosis. From measurements of a cell sample, we want to tell a malignant tumor from a benign one. Here, choosing the wrong model, or the wrong yardstick, isn't a business cost. It can cost a life. So think carefully about the two mistakes. A false alarm, calling a benign tumor malignant, leads to an extra biopsy and some worry. Unpleasant, but recoverable. But a missed cancer, calling a malignant tumor benign, can be fatal. Those costs are wildly unequal, so accuracy is the wrong goal. What we must maximize is recall, the fraction of real cancers we actually catch. Here is the real dataset, 569 patients, each described by 30 measurements of the cell nuclei, radius, texture, smoothness, and more. About 37% of the tumors are malignant. 30 features and only a few hundred patients, small, and high-dimensional. That shape will favor a particular kind of model. Baseline first, as always. The lazy rule here, call everything benign. Because most tumors are benign, that scores 63% accuracy. On paper, not terrible. But look at the cancers. It catches none of them. Recall is 0. A model that misses every cancer is worse than useless, no matter its accuracy. Every real model must do far better on recall. Our contenders are the classical models you now know. A decision tree, naive Bayes, k-nearest neighbors, a random forest, gradient boosting, logistic regression, and a support vector machine. On tabular loan data, the tree ensembles won. On text, the specialists won. On this small, continuous, high-dimensional data, who wins here? But first, a crucial pre-processing step. These 30 features live on wildly different scales, an area in the hundreds, a smoothness near 0. Models that rely on distance or margins are dominated by the largest scale feature unless we fix that. So we standardize. Watch what it does for the support vector machine. Unscaled, its recall is just 0.81. Scaled, it leaps to 0.95. Same model, but scaling unlocked it. Now the fair contest, scored on recall. The single tree and naive Bayes trail, near 0.88. The forest, boosting, and k-nearest neighbors reach about 0.93. But logistic regression and the support vector machine climb highest, around 0.95. On small, high-dimensional, continuous data, the margin-based models shine. Why does the support vector machine do so well? Its idea is elegant. Of all the boundaries that separate malignant from benign, it picks the one with the widest possible margin, the largest gap to the nearest points of each class. That widest gap boundary generalizes well, even when you have many features and only a few hundred examples. With the right kernel it can curve too, fitting boundaries a straight line never could. Let's see the winner's mistakes directly. On the held-out patients, the baseline missed all 64 cancers. The support vector machine misses just one, catching 63 of 64. If even that one miss is unacceptable, we can lower the decision threshold to catch every cancer, at the cost of a few more false alarms. That trade, recall against precision, is a clinical judgment, made with doctors, not by the algorithm alone. So which model do we choose here? A support vector machine or logistic regression, both margin-based, both strong on this data, and both able to output a tunable score so we can dial recall up to where clinicians need it. Notice the choice flipped completely from the lone project. Not because one model is better, but because the data and the stakes are different. That is the whole lesson. In code, it is short and safe. Chain a standard scalar with a support vector classifier in a single pipeline, so scaling is learned only on the training fold, never leaking the test data. Then score it by recall. Scale, fit, measure what matters. To recap this project. First, choose the metric for the stakes. Costly missed cancers mean we optimize recall, not accuracy. Scale your features for margin and distance models. Expect the support vector machine and logistic regression to shine on small, high-dimensional data. And pick the model that makes the cheapest kind of mistake. 3 projects, 3 different winners. Always match the model, and the metric, to the problem.